Lab 4, Circuits and Capacitors. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, to use multimeters to measure the actual values of conventional current and potential differences in circuits, and lastly to examine the behavior of ohmic resistors and capacitors. My results showed that the sum of the potential differences in the first circuit was 0, and the time constant RC in the second circuit was calculated to be 5.82 seconds. In this video, I will address the fundamental physics principles, circuits, calculations, and results I used in the lab which allowed me to obtain these results. The important fundamental physics principles used in this lab are energy conservation, which gives us a loop rule stating that the sum of the potential difference in a complete loop is equal to 0, and current conservation, which gives us the node rule stating that the current entering an intersection is equal to the current leaving the intersection. Also, these two equations are important for the lab. The first equation, delta V equals I times R, allows us to calculate the potential difference, and the equation at the bottom, Ln times delta V over delta V naught equals -1 over RC, allows us to calculate the time constant RC. Part 1 of the lab examined charge conservation and energy conservation in series circuits. First, I created a simple circuit that contained 2 ammeters, 2 1.5 volt batteries, and 2 resistors at 47 ohms and 100 ohms. To calculate the current of this circuit, I used the equation I equals delta V over R and found the current to be 0.02 amps, which is confirmed by the ammeter in the circuit. When I reversed the ammeter, it still read 0.02 amps, thus the value did not change. Next, I created an open circuit which has no current flowing, and therefore the ammeter displays 0.00 amps. The potential difference still exists from the two ends of the battery, which is why the voltmeter shows 3 volts. I created a graph that shows the change in potential difference across the circuit from place to place. The main points of potential difference change are sections A, B, C, D, and E, F. All of the points added up give us a total potential difference of 0 because we completed a full circuit going back to the point origin, which proves the loop rule. The ammeter reading does not change with the addition of a voltmeter because the voltmeter only measures the potential difference in voltage. Voltmeters have infinite resistance, so they do not change the current. For my potential difference measurements and the current measurements, I calculated the resistance of each of the following circuit elements using the equation delta V over I, and these resistance values are shown below. Part 2 of the lab examined RC circuits with capacitors. First, I created a circuit with a battery connected to a 10-ohm bulb and a capacitor. This circuit charged the capacitor. The light is initially bright and dims until it goes off when the capacitor is fully charged. This demonstrates that as the capacitor gains charge, the current moves slower and slower through the circuit until it stops. I then disconnected and removed the battery, which discharged the capacitor. As the capacitor discharges, the light is initially bright and then dims over time as the current is reduced to 0. The current is flowing in the opposite direction because of the charge orientation in the capacitor. I also repeated this process for a 20-ohm bulb. The current slows down and eventually stops which is shown by the movement of charges in the capacitor. The 10-ohm bulb charged in 10.17 seconds and it discharged in 10.20 seconds. The 20-ohm bulb charged in 19.83 seconds and discharged in 20.16 seconds. The 20-ohm bulb takes approximately double the time of the 10-ohm bulb, which makes sense because it has twice the amount of charge to transfer. I recorded the time and voltage of a discharging capacitor connected to a 30-ohm bulb. I graphed Ln times delta V over delta V naught versus time. I used the slope of the line to calculate the time constant, which was found to be 5.82 seconds, which is very close to the expected value of 6. This error can be attributed to relying on the hand to stop the clock each time and the use of an idealized circuit. Question 1. An actual ammeter in real life would have more resistance than an ideal simulated ammeter. Because of this, the actual ammeter would show a lower current reading than the ideal ammeter. Question 2. Our ideal model would predict the charging of the capacitor to occur instantly, but this would not be the case in real life because there would be internal resistance in the real battery, capacitor, and wires. This would result in a non-zero resistance in the circuit, increasing the time to charge the capacitor. The fundamental physics principle of conservation of charge and current were observed in the lab. The results show that the sum of the potential difference in the circuit is 0, and the RC time constant was calculated to be 5.82 seconds, which is close to the expected value of 6.